I think we're recording now. Oh, there it says recording has started. Okay. So thanks everybody for being here. And today I will give you an introduction to energy generation modeling in PVLIB Python. So this is a Python-based package. And I believe you can't really see me, but you can see my screen, my second screen, as it turns out. And here on the second screen, this is just showing my documents folder, and I have a WP folder, which stands for WinPython. And you can see the zip file that I distributed to you or made available to you for download here. Not using that, but the WinPython installation and instance is this WPY 64-31050, and the 31050 is referring to the version number. So once you get this zip file unpacked, you should have, in Windows, you should have the same file arrangement that I have, which has these mostly executables here, including Jupyter Notebook and Jupyter Lab, which are quite popular. I haven't used them very much. I think I mentioned that I use Spider, and those are both generally IDEs, or integrated development environments, and I assume this is also this IDLE. Some of these other programs that you'll see in here, I think IPython Qt console and Qt are at least sometimes related to the generation of graphics in Python. You can probably tell by how I'm talking that I am not a full expert in Python, but here to be able to give you at least an introductory tour of the software. And then for those of you who are used to command prompts, and for example, Katerina's using, working towards using Linux for this software package, in which case probably a lot of that installation would happen from the command prompt. There are some command prompts here as well. And then, I don't know the details of these folders, but you can certainly look through them and familiarize yourself. And once again, the nice thing about WinPython is that it does not install as a software program. So it runs entirely out of a folder, which means that in principle, I've been able to just zip up this installation of WinPython that already has the PVLIB package and some other necessary programming packages added and installed. And by you unzipping the file folders, you will also have the same configuration. So if you have questions or comments, please just feel free to raise your hand, or if I don't see your hand raised, then just go ahead and chime in. So I mentioned that in my case, I wanted to create a spider like icon for launching. So I have that on my toolbar here, and in this case, I guess I can see, I can right click to choose the properties. Where are they showing up? They're showing up on my first screen, but I can bring them over. So it just shows the path to the program, and the start in folder is the WinPython like root folder, which is typically a pretty convenient place. So, okay. So I do have Spider open. On my computer, it takes, maybe a minute or two to open. And I can show that to you briefly here. This is, again, it's, what I refer to as an integrated development environment. So the basic layout here is there's this area over here that's useful for, I'm not sure what this is right here, but useful for this is where you like basically type in, or if you're pasting code in, you paste in the code here. There are line numbers, and you will start to see as you add packages that you will get some useful messages. Sometimes frequently they're like error messages. And those of you who are really new to this particular programming language, this what we call the hashtag symbol or number sign is the prefix that you use for a line that is just a comment. So it won't be acted on as code. So that's a comment for intro tutorial. This is just an untitled program that I've opened right here. I have a couple other programs that were written previously that are open, but not being shown here. In the lower right is what we refer to as the console. And the console is where the messages and output from the program appear when the program is running. And you'll see the last thing I put in here was a reset to clear all the variables, and so I did that. In the upper right here, by default, you have a few options. Help, Variable Explorer. This is really useful when you're running a program because you can you can access the values of all of your variables based on their most recent time being written to. And output plots can appear here as well. And actually, I don't really know. Well, it looks like files is maybe recently used files. And so .py in Windows, .py is the default Python extension. So those .py files are going to be text files, readable by any text editor. And the other thing to note is that at least for Outlook and probably for many software packages, if you try to attach a .py file to email it to somebody, it'll be rejected or filtered out because it's considered a risky file that can run commands and let's say, do nefarious things to your computer. So the way around that is to just rename it to like a .txt file or something other benign file, and then you can email it, and the other person can just change it back to a .py if they want to use it that way. Okay, so I'm going to go to, I'm going to bring my web browser over here and maximize it. And you'll notice that I'm starting here at a web page that's called pvpmc.sandia.gov. And Sandia is one of our U.S. Department of Energy national labs. It's in New Mexico, and this PVPMC stands for Photovoltaic Performance Modeling Collaborative. So that's something that started at Sandia, and you can see it's described here as an industry, a national laboratory collaborative to improve photovoltaic performance modeling. And I think basically the people who started this work, they are, or maybe most of them still are, Sandia employees. They are generally accessible through various avenues. And if you look down here, I'm just scrolling down, about the modeling collaborative, it tells you a little bit more about it. And their goal to assemble and organize the most complete, transparent, and accurate set of information about PV system performance modeling. And you'll see here they mention like friendly support, and it's true when when you contact them with a question, they will do their best to reply in a helpful way. Obviously, the world is a large place, and there are quite a few people working on this software package, so they probably prefer that you not contact them directly all the time for every question. But I'll talk about some other resources that you can use. Um, this is the email address for Joshua Stein. He leads this particular project, and I'll just note also that if you get further into this and want to participate in the PVPMC, there's an annual workshop that it looks like the workshop is going to be held in May. It's here in the United States, and it looks like the abstracts were due just this week. I've never been to the workshop. I'm sure it would be pretty interesting and enjoyable. But what I want to do next is just show you these modeling steps here. So if you look at the modeling steps, there's an outline here. And really, what we're talking about here is setting up a model for, it could be for a solar panel with a micro inverter. So together, those two things can make a system. It could be for a regular solar array that has somewhere between, for example, 10 and who knows, maybe 500,000 panels. Um, and the power electronics that come into play, those are referred to as inverters that will normally convert the DC power to AC power for coupling into the electrical grid at 60 hertz here in the US or 50 hertz most other places in the world, I think. I'm assuming it's 50 hertz in Serbia. And what is the wall voltage if you plug something into the wall in your home? Is it closer to 100 volts or is it closer to 200 volts?
220.
220. Okay. Yeah. So that's
220, yeah.
also, I think that's also common in Europe, right? So, but in order to, let me see here. Hold on just a second. If I go home, yeah, so I'd kind of like to stay on this. Let's see if it'll stay there if I click on that, but it's a little hard. You can't see everything on this image, unfortunately, but you can see the setup here. You've got solar panels in an array. They are going to be at some particular tilt angle relative to flat. They're going to be facing in a certain direction that we refer to as the azimuth angle. If you think about the azimuth angle, you can think about that as pointing north would be like 0 degrees azimuth angle, pointing south would be 180, pointing to the east would be 90 degrees, and so forth. So you can you can set the angle of orientation. And then, once you have a solar array that exists, typically people are siting that solar array in a specific location on Earth. And once you set the location, that's going to do a couple things. That's going to determine the path that the sun takes across the sky for every day of the year and every time of day. And it's also going to define a local clock. So normally when you're modeling solar energy generation, you want to know, like, how is my array going to be performing at 9 o'clock in the morning or at 1300 in the afternoon, for example. So you want to make sure that the clock that you're using for modeling is correct for your local time that you read on the clock. And then most importantly, perhaps, or not insignificantly, your location is also going to define what you might refer to as the climate, but maybe more descriptively as the typical weather patterns that you see. So, one of the things you can imagine, let me just take this little detour actually. So, when you think about the weather, first of all, um, the weather is going to, the weather as it pertains to a solar array performance is going to determine, for example, whether it's a cloudy day or a sunny day or a partly cloudy day. It's going to determine the temperature. It's going to determine the humidity, which can play a role in how much sunlight is scattered as the sunlight comes through the atmosphere. It's going to determine the wind. And yes, the presence of wind can make a difference on solar array performance through the fact that the wind, can lead to convective cooling of solar panels that heat up in the sunlight, for example. Um, Definitely the most important parameter for the performance of a solar array is what we call irradiance. And the irradiance is it's really the intensity of the sunlight incident on the array. So these are the most important effects. Let me see here. Okay. All right. So other things that affect your performance, certainly, how much sunlight is hitting the array, including off the ground, how much of the sunlight is direct, how much of it is diffuse coming from the blue sky regions. Number three here you'll see is shading and soiling. So if you unfortunately have, a tree, for example, or a building that may block the array partially at some point in the day on some days of the year, that certainly will have an impact. Soiling, in an array that's in front of our building, we see a little bit of dust buildup, usually in the winter, because we put some magnesium chloride on the streets to help melt the ice and snow, and that ends up as dust that can, impact our solar production. The rain washes that away. Most solar arrays are not cleaned intentionally, but there are places where rain is so infrequent that cleaning can be economically useful. And so yeah, so I think I mentioned that the solar cell temperature will affect the performance, and then really you can get an output in terms of the DC voltage, which is sort of on the solar panel side, and then you go through an inverter and connect into the AC grid, and the performance of the inverter makes a big difference for reasons that will become clear. Okay, so this is the PV Performance Modeling Collaborative. It's also the place where you can go to get your software. Let me see here. So okay, all right. So actually, I don't see it right now, but these are some of the supporters here. I'm sure you recognize some of them. A little surprised that the Department of Energy, of course, is a big supporter, but the U.S. Department of Energy. Let me go. This is home, document library. So here's the PVLIB toolbox for both for Python and for MATLAB. I do not use MATLAB. I have used it before, but I don't use it now. So that's another route you can go. And then there are download links for the PVLIB Python package. As I mentioned in my email, this has already been installed for the WinPython distribution that I gave to you. But you can download it here from GitHub, and I think I mentioned also that the documentation is on Read the Docs. So I already had that open in another window, but this brings you to Oh, it says here this document is for an unreleased development version. Documentation is available for the current stable release, which is what I recommend you use. So here's the stable release, and I can close this down, I think, because this is a duplicate. So right here is the opening screen for the PVLIB documentation. And you'll notice the website address is readthedocs.io /en, I believe refers to the fact that this instance is in English. And then if you scroll down here, you'll find a link to the user guide. And the user guide has, has all of the detailed information about this software package. And, there's the package overview, including the introduction, so-called user extensions, how to get support, how do you contribute if you're a software programmer, a Python expert, and you get interested in this, you can contribute your own functions and capabilities. And there's a section here on installation, so that if you're installing this package using Anaconda or a Linux-based Python installation, then this should be helpful right here. Okay. So I'm going to go ahead and scroll to the bottom here because we're not going to spend time on this. And then this then is the tutorial. So the tutorial talks about different modeling, they call them paradigms. So a paradigm is really an approach to modeling. And, it says here, the backbone of PVLIB Python is well-tested procedural code that implements PV system models. It says it also provides a collection of classes. So now that is software language that, or programming language. And, I have some general ideas about this, but I'm not a software programming expert. But it provides a collection of classes for users that prefer object-oriented programming. These classes can help users keep track of data in a more organized way, provide some smart functions with flexible inputs, and simplify the modeling process for common situations. Classes don't add any new algorithms beyond what's available in the procedural code, and most of the object methods are, as they say, simple wrappers around the corresponding procedural code. It says, let's use each of these PV modeling paradigms to calculate the energy yield for a given hardware configuration at a handful of sites listed below. So I want to, we can do that. We will do that a bit in, I don't want to click that. Let me see here. Give me a second. Let's see here. We will do that in Spider. We'll do some of that in Spider. But before we do that, I wanted to show you, I'm not sure how many of you are familiar with Google Groups, but I'm logged into Google. When I go to groups.google.com, I can look at my groups. And one of my groups is this PVLIB Python group. And PVLIB Python, you can see it has 743 members. And, I get an email when people ask a question. I think there's an option to have like a daily digest or maybe even a weekly digest of questions and, answers. But one of the things that I'll just point out here is, let me take one more detour and then I'll come back to this PVLIB Python groups. So I mentioned the idea that a certain location on Earth, whether it's Belgrade or Toledo or, San Francisco, California, or Sao Paulo, Brazil, will have typical weather patterns, right? So we know that every year is different, and we know that there are big extremes. There has been developed this idea of the typical meteorological year, which is abbreviated as TMY. And it says here, this is the Wikipedia, it's a collection of selected weather data for a specific location listing hourly values of solar radiation and meteorological elements for a 1-year period. And I can tell you that you're most likely to use this TMY3 data, I believe. But I think that these are still really US focused, because you can see here there are many locations in the US, and they include some US territories. But there are data sets available for typical meteorological year weather for other locations on Earth. Let me just, though, take this opportunity to explain how the TMY3 data is put together. When you look at the TMY3 data, what you'll see is that each 1 month is a month of actual weather readings, historical weather readings, and that a typical TMY3 year will include monthly weather readings from different years. So, for example, January might be from 1998, February might be from the year 2001. And so these are kind of identified as typical months and put together to create a typical year. So I mentioned that you can find weather files for other locations on Earth, and the reason I know that is thanks to this PVLIB Python, because on March 1st of this year, a question was asked. I was wondering which sites provide the best TMY databases. For my research, I want to have TMY data for various locations around the world. I now use PVLIB, but some locations like Buenos Aires, Argentina, it raises an error. And it talks about another resource for weather. And there's an answer here that says, try here. And there's a website. It says the keyword they use for TMY is climatology. And they have results for any arbitrary site across the globe, including offshore sites. Okay, so and then there's another answer here that says, it looks like there are a few answers here. And so, these are examples of people trying to get this working. And so, you have help and resources. And so sometimes it takes a little bit of, determination and dedication to get past some initial challenges, but typically there are avenues forward. Okay. Any questions to this point? We haven't really started any of the programming yet, but does anybody have any questions? Okay. So if you have two screens, then I would suggest that you open this link on one of your screens. I can put this in the chat to make things a little bit easier if you haven't done that yet. There's the link in the chat. I'm going to move this over to my first screen, and that leaves this Spider program here. And what I'm going to do, and I think that Spider and or the Read the Docs has improved this behavior a little bit, but I'm going to select and copy the first 3 entries from, well, let me just show this quickly. So you'll notice that the way this is set up is as if you're typing these into the console. So it's got this, in 1, input 2, input 3. But I just selected these first 3 lines, and I'm going to hit Control-C to copy. And I'm going to come over here to my code where I've opened an untitled. So under File, you can do New File. Okay, it shows up as untitled initially. I've typed in the comment for intro tutorial, and I'm just going to go here and paste those 3 lines in. So what's happening is you're telling the program to import these 3 packages. So PVLIB and Pandas. Pandas is something that is a software package that introduces something called data frames. And data frames are uh, they're um, they're sort of like an array or a list, but they're a little more powerful than that. And this as PD just means that when you're programming, you can abbreviate pandas with the letters PD. And then you're also importing matplotlib.pyplot as PLT. That's a plotting package. So at this point, you can say, save as. Um, I'm going to put this in, I guess, this folder right here. I'll call it Python Code 2022. The way I tend to name my files is with the 2023-0309 so that the files come up chronologically when I sort them. And I'll just call this PVLIB Python introduction. Okay. And then save. So now you'll see this file has a name up here. There's nothing really to run so far. I mean, I could run it, and these little triangles are saying like, you've imported this, but you're not using it, well, we will use it because I'm going to go back to the intro code and just copy in a few more lines here so that you can see the program start to come together a little bit. So what do we need to be able to model a solar array? Well, we need a system design, we need a location for it, and then we need a series of like times. And then of course we have to decide like what output are we looking for? What output are we interested in? So, what's shown here is a comment, latitude, longitude, a name for the location, the altitude, which is in meters, and then the time zone. And you'll notice here we've introduced what I will call a variable, coordinates, and it has this format with a square bracket and then these indented lines in parentheses that have latitude, longitude, a name in single quotes, an altitude in meters, and a time zone. And you can see the time zones as they're listed here are relative to Greenwich Mean Time, +7 hours for Tucson and Albuquerque, +8 hours for San Francisco. And you can see Berlin is also listed here, and GMT -1. And so at this point, let me go over to the right here and click on Variable Explorer. So nothing shows up here right now, but if I were to run this program, it would do almost nothing. But I ran the program, and what I do see in the Variable Explorer list is that the coordinates variable shows up. Its type is shown, its size it has 4 different locations. And this shows some of the values. If you double click on this coordinates, it opens up the full access to the data in that list of coordinates. And so, it's got indexes 0, 1, 2, and 3. The type is called a tuple. Their size is 5 because they've got 5 elements here, and it shows you the values. So I'm going to go ahead and close that and come back over here. And I'm going to go ahead and grab a bit more of the code. Let me see here. Okay, so there's, this is the example to kind of show how this software package works. So here's another comment, right? Get the module and inverter specifications from SAM. Now, SAM is not something that you really need to know to be able to use this, but SAM stands for System Advisory, or I think System Advisory Model. And I actually don't have a full appreciation for what SAM does, but I believe that it was a modeling tool developed possibly at the National Renewable Energy Lab, which is in Golden, Colorado. I used to work there a long time ago, but so I think that's, kind of a throwback to that particular system advisory model. What you'll notice here is there's a variable that's thrown in here called Sandia modules, and it's set to this value pvlib.pvsystem.retrieve sam Sandia mod. And so what that's doing is it's going to read in probably a pretty big database of module information, module, model numbers. These are solar panels. I'll just mention also that Sandia mod is not the only, it's not the only database of solar panels. And the way panels are defined in each of those databases, they're different from each other. Similarly here, we have a retrieve for CEC inverter. And I believe CEC stands for California Energy Commission. So that just happens to be the name of the inverters database. And then from that database, we're defining a specific module. So our module type is going to be this Canadian Solar CSP5 220M 2009. You'll see it's got like 3 underscores here. You have to be precise when you're defining them. If you're going to type that in, you got to make sure you type it in exactly so that you find the module that you want. The inverter then is an ABB microinverter defined by this name right here. There's also a line of code for what's called the temperature model parameters. And if you hover, let's see, actually, okay, so this, this is pvlib.temperature model parameters, SAPM. It's saying here that this is, open rack glass. So I think open rack just means like ground mount, not rooftop mount, so that the air and wind can get to both the front and back of the panels, and that this particular solar panel is being modeled with glass front and glass back sheets. So, similarly, I can run this file again up here, the green triangle. By the way, when you run the file, it will save the file. So normally you don't have to worry about losing that information. So now when I run the file, the output is really just telling me what it's running and what the working directory is. There's no output per se, but you'll notice that our variable explorer shows more variables now, including the Sandia modules variable. So, one way to see if a module type that you're interested is in here is, is to, well, actually, it would be very inefficient to look through these, but these are, it looks like the module types are shown here as the first row in the column, and it tells you the year, the area in square meters, what type of panel it is. This is multi-crystalline silicon. It has 72 cells in series. This one has 60 cells. Yeah. Did you have a question? Okay, I'll keep going. But so you can see there, we're just in the A's here, and there are going to be something like 500 and, 500 and I forgot what it said, 23 or something altogether. So looks like it'll keep populating them, but by far a better way to access this is to see if you can figure out how to export all that data into like an Excel file that you can search more easily, and then you can find whether or not your module is included. And that's a Python trick where you've got this inverter Sandia modules that has all this information in it, and there are Python tricks to just dump that contents of that data frame into an Excel file or a CSV file, I guess is probably what it would be. Similarly with the inverters, it looks like there are, I don't know, is this right? 3,264 different inverter models. That's a lot, right? All these ABBs, and you know if we'll get past there's many different manufacturers. It looks like Energy Industries is one. I don't know why I can't click on that, but I'm not allowed to click on that. Okay, so um, uh, interesting. Okay, so these next lines of code have to do with pulling in the weather, and the introductory well, let me just show this briefly. So this web page that is the user guide, you know, it has some narration in here, right? About in order to retrieve meteorological data, we can make use of the IO tools module. In this example, we'll be using PVGIS, one of the data sources available, to retrieve a typical meteorological year, which includes irradiance, temperature, and wind speed. Okay, so we can see what it does include. Did I copy it over? I did copy it over. So it's down here at the bottom, and it has, you know, it defines an empty list. So it defines a variable that's an empty list, and then for location in coordinates. Okay, so um, uh, each of these four are implicitly locations, and the coordinates variable is here. So for each location and coordinates, you know, you're going to grab these values, and those values together give you the location. Um, and um, and the weather then is for each of these locations is obtained through this get PVGIS underscore TMY as a function of latitude and longitude, and mapping the variables is set to true. And if you want to get more information about this, let me see if I actually, when I hover over this, I thought it would give me more information. Okay, so I can hover over this, and up will pop this get PVGIS TMY. And it says for more information, see the PVGIS TMY tool documentation. But it does have some basic information here about the variables and their formatting and so forth. So you can dive deeper into what any of these functions, you know, what their inputs and outputs are, and what their presumptions are. And then there's this weather.index.name is equal to UTC time, and then TMYs is this variable up here, dot append weather. So what you're going to see after I run this is that the weather is going to appear in this TMYS. So I'm running it, and oh, let's see, actually, looks like it's still running. So it finished successfully with no errors, which is good. And it did indeed populate this TMYS, and it also populated weather. And I think that the weather is going to be just the most recent instance of weather. So I'm guessing it would be the weather for Berlin. Maybe we can tell by looking at it. Um, let's see here. So let's see. The year for this particular month of January was 2016. These air temperatures are going to be in Celsius, so it looks to me like it could be Berlin. It's going to be a little bit hard to tell from just the weather, but this is March 5th. The month of March came from the year 2014. It's getting a little warmer, the humidity. And then I don't know that I talked about these in detail, but GHI, DNI, and DHI are different components of the irradiance, which is the solar intensity that is incident on a receiver, or like a solar panel, or a pyranometer that measures irradiance. And so One special case is GHI, which stands for Global Horizontal Irradiance. And just a reminder, do I still have this open? I do. Just a reminder that if you want information, as you're learning more about this, you can go to this pvpmc.sandia.gov, and you can look at the modeling steps, and there's direct normal irradiance, global horizontal irradiance. So GHI, this is the amount of terrestrial irradiance falling on a surface horizontal to the surface of the Earth. So it's really a flat receiver. You'll notice here it says terrestrial. That means that we're not talking about the intensity of sunlight above the atmosphere. We're talking about it on the surface of the Earth. I'm going to pull that back out, and give me just a second here, and go back to where we were in Spider. And I'm going to go ahead and close. Well, actually, so GHI, DNI is direct normal irradiance. So on a sunny day, if you point your solar panel or your power detector directly at the sun, that's going to give you direct normal irradiance. If you block the diffuse irradiance, which is everything, all the other light that's coming from like the blue sky regions. And DNI has a definition that you're within like 2.5 degrees of directly looking at the sun, because there's a lot of scattering included in that first 2.5 degrees. DHI stands for diffuse horizontal irradiance. So the diffuse component is everything that's not the direct component. So on a cloudy day, DHI, DHI will be, high on a cloudy day, because most of your light is coming from is diffuse. And then there's wind speed in meters per second. There's a wind direction, probably in degrees relative to north. My knowledge of meteorology tells me that if the wind direction says it's north, that means the wind is coming out of the north towards the south, but you have to verify that for yourself. And then there's pressure here also. So it looks like this is a relatively limited, actually, let me see here, a relatively limited set of data, only 9 elements. If you look at TMY3 data, sometimes you'll see many more elements included in the weather. And then all those the weather values for these 4 locations will be combined here. And when you look at this, you'll see there are 4 different weather files for the different locations. You might recognize this 8760. That's the number of hours in the year, because let me see if I can actually bring this up. Okay, so I can bring one of those up by double clicking, and you'll notice that the weather data is for 1 hour intervals throughout the year. So there are 8,760 hours in a year. Okay. So we haven't really gotten to, fully to where we're going yet. Let me see if I can find here we go. But we're getting closer. We haven't really defined our system yet. We have a module and an inverter. So I'm going to go ahead and copy, I guess, a bunch more stuff in here. And this is, okay. So a bunch more code is going to be dropped in here. And this is actually, give me just a second here. Okay, looks good. All right. So this is the procedural approach to modeling energy generation. Our system is now defined. We have like a single module. We have a single inverter. It's called a microinverter. And we have defined the surface azimuth. And I mentioned the azimuth concept earlier, but let me show you let me show you again. See what this place has to say about that. So let's see here. Array orientation. Okay. So, an array orientation is an important input, that's for sure. It's usually going to be described as either fixed tilt or tracking. So we're talking about a fixed tilt array, does not move. And the array orientation then is described by vectors of the array tilt, which is relative to flat. So 90 degrees would be a vertical module. And then the array azimuth angle is going to be the direction that the face of the array, the normal to the panel is facing if you project the normal straight down onto a horizontal plane. So it doesn't have a picture here actually, but array orientation areas. Well, it sort of does. So the array azimuth you can kind of see there. Okay. All right, let me pull this off. And so our system now has been defined because we've chosen a module and a microinverter, and we have a surface azimuth. What we don't have now is the tilt, but we're going to define that still. So we have, I forgot what these curly brackets are. Somebody can chime in if they recall, but this is, it's like a list, but slightly different, but it's going to be where all the energy generation values are stored for the 4 different locations. So again, for each location, I don't know what this means actually, weather in zip. But you've got latitude, longitude, name, altitude, time zone. You're defining the surface tilt for each of these locations to be identical to their latitude. And the latitude information is included here. So the first one is the latitude. So that's how far north we are. And you can see here, Berlin is the furthest north by far. San Francisco is second furthest north, and the furthest south would be Tucson, Arizona. Okay. So if I scroll back down, the latitude is going to be what's used for the surface tilt. So you're going to be tilted at latitude. That's kind of a good starting point, but is typically not the optimal for annual energy yield. And now we're going to go through some very detailed, information here. We're going to calculate the solar position for every time period in the index, which is every hour. That's going to depend on the latitude and longitude. It's also going to depend on the altitude to some extent. So that's included. And the solar position will depend on the temperature. And the reason for that is that when you look at the position of the sun in the sky, there's actually some small effects associated with refraction of the atmosphere. And so this is a very detailed calculation, if you will, that takes into account temperature and pressure. It turns out that so this is direct normal irradiance extra. So that's referring to extraterrestrial. So it turns out that in the sun's path around the Earth, the distance between the Earth and the sun changes slightly. And so the intensity of sunlight above the atmosphere changes slightly. And so that is taken into account in determining the behavior and energy yield of a solar array. Because if you start with more sunlight above the atmosphere, then in any given weather conditions, you'll also typically have more solar irradiance reaching the Earth. Air mass has a very specific definition. It's the effective thickness of atmosphere through which the sunlight is passing. So air mass is going to be equal to 1.0 for when the sun is directly overhead, for example, on the equator at solar noon. There's some information on pressure here. There's the air mass absolute. There's the angle of incidence. There's the total irradiance that depends on surface tilt, surface azimuth, apparent zenith that takes into account refraction, and then the weather. So, was it a cloudy day? Was it a sunny day? What are these values for these different irradiance components? And then there's the extraterrestrial direct normal irradiance, and then there's a model that's being used to, there are several models you can choose from. This model is called Hay Davies, and it will calculate this total irradiance value. There's a model for the cell temperature that's going to depend on the wind speed. It's going to depend on the air temperature. It's going to depend on the global plane of array irradiance, which is really the key for generating solar power also. There's also effective irradiance, which is going to include POA direct and POA diffuse. Oh, I see. Those are the inputs. That's in parentheses. And then you've got a DC value for your energy, and you've got an AC value for your energy that depends on the inverter. And then the annual energy is going to be the sum of the energy generated in each of your 8,760 one-hour periods. And then, energy's name, if you go back to name, that's up here, Tucson, Albuquerque, San Francisco, and Berlin. And so, and then you're going to put the energies into a pandas database series. And so if I run this, we're still not going to get a plot, but we'll get some values for the annual energy. And so this is running right now. Hopefully we won't get any errors. I'm almost done. Okay, so it ran. So our energies should be updated. And this is just going to tell you the units here are going to be watt hours. And power times time has units of energy. On our electric bills here, we pay for kilowatt hours in terms of consumption of energy. So 435.9 kilowatt hours for Tucson. Albuquerque's even better, 449.9 kilowatt hours. San Francisco is lower, and Berlin is the lowest of these four. So, all right. So then if I go back to, we're almost done with this example. The wrong one. I am all over the place. I'm not finding what I'm looking for. Here we go. All right. So I stopped with that. So, it says, you'll see in the next bit of code here, to finish this procedural example. Okay, so in this next bit of code, it says, based on the parameters specified above, these values for energies are in watt hours. Okay, and so, I didn't do this print energies, but that would be the output. In fact, that matches what we looked at before. So I'm gonna delete that stuff because that's not part of the code. That's part of the output that copied over with the code. And then, so is this also, that's output. And so is this last one, that's output. Okay, so now if I run this, we should hopefully get something that's more visual in terms of results, where we don't have to just dig through the variables. And you'll notice down here when it's done. So it outputs these energies that we just looked at in the energies variable. And if you click on plots, it made a bar graph with, yearly energy yield, watt hours, and then it names these different locations. And so you can copy that image, you can change the size of that image, you can control the colors, you can do many things if you dig into the Python capabilities in a little more detail. So it's got to be hard to listen to someone talking about software programming. So I'd like to stop here and I guess maybe hear your thoughts and questions. Is anybody awake?
Yes.
Me too.
Yes, of course. Thank you, Randy.
Yeah, you're welcome. I mean, I can definitely show you one other example without going through it in as much detail. It's more of an actual solar array. But first, let's see if there are any questions, comments, discussion. Yes, Stanko.
Yeah, thank you very much. If there is any student want to ask question, I'll give them priority. If not, right. It's a very interesting piece of software. And well, I want to ask a question, but well, I'm not sure I can formulate it very precisely. So how I see this piece of software at the moment, it is solving some sort of direct problem. What I mean by that, so I can easily imagine tomorrow one PV engineer go to the place, let's say San Francisco. He knows everything about geographical location. He knows everything about atmospheric kind of profile of the place, or software knows about that. And then this engineer will probably, based on his engineering intuition and determination, out of those 3,000 inverters and I don't know how many PV different panels, he will make kind of combinations, and then he would decide what is the best kind of system to be installed at the place.
Mm-hmm.
Now, how I can see this, and this is probably a question and probably for discussions. Well, this is kind of problem for so-called typical reverse engineering or inverse problem, how we call it in software development. Now, obviously, either customer in San Francisco or this software engineer want to choose the best hardware or the, I don't know, to optimize the system in the way to produce the best efficiency and cheaper electricity for the customer. Now, is there any plans to do so? Because in terms of software development in the next stage, even that it's 3,000 different inverters, so how many new inverters would be designed in the future? It can always be updated database of that, and solar panels and with their characteristics. I mean, computers helping us and are very good for those things.
Yeah, so I'm not sure I understood your question, but it sounded like maybe you were asking whether or not the software package could serve the role of simply by defining a location and maybe the total area that you had available to you, maybe running kind of a full modeling scenario, or almost like maybe not quite artificial intelligence approach, but to come out with an optimal system design.
Yes, inverse system design. Yeah.
Yeah, that's an interesting question. And I would like to hear the developers of this software package answer that. And it makes me think about the the fact that there are, for some of the really important aspects of this modeling package, there are different models that you can select. For example, for right here, for example, line 81,
Mhm.
You're modeling using Hay Davies
Yes.
when, Mike, what we might ask is, well, what are the other models and which one is the best? And I don't have any preference one way or the other, but maybe some people do. Probably the people involved in making the models have maybe argued about, whose is best or when it's the best, or I don't know. So yeah, it's a really good question. And what's also interesting is that you can make a model of a solar array and run the model and get a certain value for what you expect. But it turns out to be very difficult to validate that with real world data. And I think the challenge there comes into somewhat in terms of maybe the subtle variability in parameters like cable length, or maybe the quality of the AC electrical grid can make a difference. But maybe more importantly are things that are difficult to measure, basically. Like, are you able to measure soiling losses? Are you able to measure mismatches between the performance of the modules that are in series in a string, because that'll have an influence. And so ultimately, I think that, typically when you run a model, you're maybe less likely looking for, getting within 0.5% of the actual performance of your array, and you're more likely looking for dependencies on the things that you're talking about, right? Which might be like the tilt and the azimuth. And but Stanko, I can tell you that a lot of times people are using this software package they're starting to bring in energy storage. They're starting to bring in